Hello everyone, welcome to Dreamers.
In this video, we are going to discuss some problems from Postulate 1. First question is, which of the wave functions in figure cannot have physical significance in the interval shown? Why not? In order to solve this problem, we have to go to the earlier video, where we have discussed regarding the wave function. That is, for the wave function to be physically meaningful, it must be continuous, finite, and single valued. The volume integral of probability density must be finite when you integrate from minus infinity to plus infinity. The derivative of psi with respect to x, with respect to y, and with respect to z must be continuous and single valued everywhere. So by applying this, we can easily find out which of the wave functions in this figure cannot have physical significance in the interval shown. In figure A, the wave function appears to satisfy all the conditions over the interval shown. So it can represent a valid wave function. However, since its slope since its slope is 0 everywhere, which is technically inconsistent with the uncertainty principle. Nevertheless, this point may be overlooked in simpler analysis. In figure B, the wave function is not single value. That at this point you will find two value of the wave function, which violates one of the essential conditions for a wave function. Thus, it cannot represent a valid wave function. In figure C, the wave function fails to satisfy the condition of a continuous first derivative, which disqualifies it as a wave function. In figure D, the wave function does not meet the requirement for continuity or a continuous first derivative. Additionally, one can suggest the wave function goes to infinity, though this is not clearly evident from the diagram. Therefore, it cannot represent a valid wave function. So, next, in figure E, the wave function satisfies all the necessary conditions, including being single valued, continuous, and having a continuous first derivative. Thus, it is a valid wave function. In figure F, the wave function is discontinuous, which violates the condition for a quantum mechanical wave function. Now, another question, which of the wave functions in figure cannot have physical significance in the interval shown? Why not? In figure A, the validity of the function is yes, because the function is single valued, continuous, and has a continuous first derivative, satisfying the necessary condition for a valid wave function. For terms and condition applies that if the boundary lie from this x is equal to a to x is equal to b. In figure B, again it is conditional yes or no, just like figure A, because the function is valid if you consider the wave function as defined only on the specified interval shown in the plot, that is from x is equal to a to x is equal to b. However, if we interpret the interval to extend to the entire positive axis as shown, if you consider the entire positive axis, it becomes invalid due to the apparent discontinuity at the end point. In figure C, it is not a valid wave function. The reason is that the first derivative is discontinuous as well as the wave function is discontinuous, violating the requirement for smoothness. Additionally, it is likely implied that the wave function approaches infinity at the discontinuity, which disqualifies it as valid wave function. In figure D, it is a valid wave function. The reason is the wave function satisfies all the necessary conditions, hence it is a valid wave function. In figure E, it is not a valid wave function because if you consider this point, then the wave function has three values at this position. It is multi-value or it is not a single value. Hence, we can say this is not a valid wave function. In figure F, this is a valid wave function because it satisfies all the conditions. Next question is, which of the following wave functions cannot be solution of Schrodinger's equation for all values of x? Why not? So there are four wave functions. First one is psi is equal to a sec x, psi is equal to a tan x, psi is equal to a e power x square, and psi is equal to a e power minus x square. So the wave functions 1 and 2 are both infinite when cos x is equal to 0, that is at x is equal to plus minus pi by 2, and at other odd multiples of pi by 2 cos x is equal to 0. When cos x becomes 0, sec x, which is equal to 1 by cos x, and tan x, which is equal to sin x by cos x, both become infinite because the wave function diverges at this point, that is at x is equal to plus minus pi by 2 and at other odd multiples of pi by 2. The wave functions a sec x and a tan x could not be the solution of Schrodinger's equation for all value of x. The wave function psi is equal to a e power x square diverges as x tends to plus minus infinity and cannot be the solution of Schrodinger's equation for all values of x. The wave function psi is equal to a e power minus x square decays exponentially as x tends to plus minus infinity and is normalizable. Hence, it is valid wave function. Next question is, find the value of the normalization constant a for the wave function psi is equal to a exponential minus x square by 2. The normalization condition requires the integration of probability density must be equal to 1 when you integrate from minus infinity to plus infinity. And now when you substitute in place of this psi, that is a exponential minus x square by 2, this equation becomes this equation. And we know that is the value of this integration is equal to root over of pi. So whenever you put root over of pi here, you will get this equation, that is a square root over of pi is equal to 1. So from this you will get a square is equal to 1 by root pi, and hence a is equal to 1 by pi power 1 by 4. So these are some problems from postulate 1. Next we will see some problems from postulate 2, 3, 4 and 5. Thank you.